Good morning, everybody. Going to give people a couple minutes to join, and then I'll start the lecture. How's everybody doing today? Thumbs up? Good morning. Going to give people a minute or two to join. Thumbs up. Woohoo! That's right. We can do thumbs up. Okay, so while people are joining, let me do a little recap of what I covered yesterday. So one, started out talking about the fact that we have been modeling forces as being constant pretty much up until now. We haven't considered forces that are really changing as a function of time. And in reality, no force is really exactly constant. So for example, if I was looking at what is the force that, let's say, this bat is exerting on the ball, we've been modeling forces that they're constant. But in reality, what happens is most real forces start at zero, they increase up to some maximum value, and then they fall back down to zero. And I showed this really cool video, and I'll show you again. So this is a video of a golf ball traveling at 150 miles per hour, filmed with a camera that can film at 70,000 frames per second. Check this out. Such a cool video. Now, this is not a real video of the real golf ball. This is basically one of those rubber squishy balls that looks like a golf ball. But the whole concept is the same. Anytime I have a real collision, what ends up happening is the object hits the, let's say the wall in this case, it starts compressing, reaches some maximum compression, starts expanding again, and then if we were to look at a real video, this is a more realistic video. But again, you can imagine if I were to actually plot the force as a function of time, it is most definitely not constant, and it looks more like something along these lines. And so what I went through on yesterday, let me just do a little recap. Starting with sum of the forces equals ma, which is m dv dt. What I did is I derived for you an equation from this. We ended up getting this integral. In fact, let me just, grab these controls for a second. Why can't controls meeting? Oh, more chat. Stop recording. Let me stop this for 1 second. I don't know why I can't. I want to mute all. Allow participants. Okay, share the screen again. So starting from Newton's second law, the sum of the forces equals ma. And again, I'm just looking at this in one dimension. What I derived for you was that the integral of fx, the force in the x direction, integrated with respect to time, some initial time to some final time, equals mass times my final velocity in the x direction minus mass times my initial velocity in the x direction. From this left-hand side is what we define as impulse. And it's basically the overall effect of the force as a function of time. We give impulse the symbol J, and I have no idea why we use J. But impulse is the integral of the force with respect to time from some initial time to some final time over which the force is acting. The end result of this impulse is it changes a quantity called the momentum. So this would be the final momentum in the x direction minus the initial momentum in the x direction. Momentum is a vector, and it equals the mass of an object times its velocity. And the units of momentum are kilograms meters per second. Now, there is no special name for this unit, so I have actually absconded this unit. For now on, the unit of impulse or unit of momentum is going to be called the joule, and the symbol is J with a little smiley face in it. Actually, I'm just kidding. We're not going to do that. Okay, so momentum is the mass of an object times its velocity. And just like any vector equation, we could break this up into x and y components. So the momentum in the x direction equals mass times velocity in the x direction. Momentum in the y direction is mass times velocity in the y direction. And what I ended up deriving for you is this impulse momentum theorem. And it says the following. One, impulse is the integral of f dt, and the impulse in the x direction is the integral of fx dt. Impulse in the y direction is the integral of fy dt. Since this is just the integral of f dt, the impulse is really just equal to the area under the curve of force versus time. And a second way of looking at the impulse is, rather than looking at the integral of the force integrated with time, another way of looking at it is looking at the average force. So here is, let's just say, a force on an object. The impulse is the area under the curve of force versus time. This is basically how we're defining the impulse. But oftentimes, I want to look at what is the average force. And the way that the average force is defined is, it's a constant force that would give you the exact same area under the curve as the real force. So for example, let's just say that here's my force versus time. So here's my force in newtons versus time. And let's just say the real force kind of looks like something like this. It increases to some maximum value and then falls back to zero. Well, if I wanted to consider the average force, so my force starts here, and let's say it ends here. The average force would be the constant force that has the exact same area under the curve as this real force. So the big takeaways from yesterday is the impulse on an object equals the change in momentum of the object. So impulse, let's just say in the x direction, is the integral of the force in the x direction integrated with respect to time from the initial to the final time. And that equals the change in momentum. So it's the final momentum in the x direction minus the initial momentum in the x direction. And that's just sort of a little recap of what I covered yesterday. Two different ways of looking at the impulse. It's either the area under the curve of force with respect to time, or it's also equal to the average force times delta t. So, impulse. Is the integral of the force, and let's just look at the impulse in the x direction with respect to time from t initial to t final, which is equal to the area under curve of fx versus t, but it's also equal to the average force in the x direction times delta t. Okay, little recap. So what I want to do is, let me stop this for a second. I think I figured out a way of doing clicker questions using polls. So I'm going to launch a poll. I'm going to share this screen again and go to clicker questions. So what I want to do is look at this very first clicker question. And it says this: two objects have the same momentum. Do the velocities of these objects necessarily have the same directions and the same magnitudes? So for example, let's just say you were told that two objects both have a momentum, and let's just say that the momentum is 10 kilogram meters per second, and it's moving to the right. So both of these objects have the exact same momentum, The question is, do these objects have to have, do the velocities have to have the same directions? Do the velocities have to have the same magnitudes? So you got 4 different choices. Haven't done this before, so I want to try just doing this as a poll. Hopefully you guys see a poll somewhere on your screen. If you're looking at this on an iPhone, you may not see it, but I want to give you just 30 seconds. What do you think? A, B, C, D, or E? And the answer is not E, just so you know. Do 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 do. Chat. Why can't I see the chat? Oh, definitely E. All right, I'm going to end this poll in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. End polling. And what we have is a slight majority say C. Do these objects necessarily have the same directions and the same magnitudes? So let's go through this. So 1, let me just give you the answer. Do these objects have to have the same directions? The answer is for this, yes. Do they have to have the same magnitudes? The answer for this is no. For a vector to be the same, the magnitude has to be the same and the direction has to be the same. So if 2 things are going to have the same momentum, they have to have the same magnitude of momentum and they have to have the same direction. So let's just say I had a 2-kilogram object. If it's moving to the right at 5 meters per second, its momentum would be the mass times the velocity. It would be 10 kilogram meters per second, and it is a vector, so I need to indicate a direction. If the second object is going to have the same momentum, it has to be moving in the same direction, but it doesn't have to have the same velocity if the masses are different. So for example, if the second object had a mass of 10 kilograms, it was moving to the right at 1 meter per second. Its momentum would also be 10 kilogram meters per second in the I direction. If this second object wasn't moving to the right, but was moving straight up, it would have a different momentum because the direction would be different. So if the masses are different, the magnitudes of the velocities can be different, but they have to be moving in the same direction if they're going to have the same magnitude. Okay, one other clicker question I want to ask. This is kind of a cool one too. So this is thinking about impulse momentum theorem. So this is 11.9. So actually, let me just stop this for a second so I can start the polling again. Stop share, polls, relaunch polling, continue, share the screen again. Okay, so the clicker question is, a paratrooper whose chute fails to open lands in the snow, he is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. Does the presence of the snow increase, decrease, or leave unchanged the impulse stopping the paratrooper and the force on the paratrooper? So, you know, you've got paratrooper obviously looks like a box and they're falling. They are about to basically hit the ground and they can either hit the bare ground or let's say there's a bunch of snow on the ground. The question is, does the presence of the snow, how does it affect the impulse acting on the paratrooper? How does it affect the force on the paratrooper? So take 30 seconds. What do you think about that? Why can't I get my poll going?
Wait, once I submit, that's it?
Dang it. I haven't tried this before, so I don't know. I don't know if you can change your answers. And in fact, I don't even know where the poll went on my screen. Why can't I open that? Okay, so apparently I can't see the poll anymore. I just minimized it somewhere. Where'd it go? Poll. Your screen sharing is paused. Why does that pause? Okay. I can't, I'm gonna have to end this for a second. Stop share. Where'd the poll go? I couldn't see the vote. Okay, so scrap that. I don't know what happened to the poll. Let me just bring this back. Screen share. Okay, so here, easiest way to think about this is, rather than looking at the impulse as the integral of f dt, if I think about the impulse as the average force times delta t equals the change in momentum, which is going to be equal to basically my final momentum minus my initial momentum. Well, as this paratrooper is falling, right before they hit the ground, they're going to have a certain momentum. And we're assuming that they end at rest. So in this case, my final momentum is going to be 0. So the change in momentum is the same whether the object comes to rest over a long time or over a short time. So the key here is the change in momentum is the same regardless of time. Right? I have some momentum right before the collision. I end up at rest. My change in momentum is going to be the same whether the collision takes place over a long time or the collision takes place over a short time. So if I think about this, then my average force times delta t is my change in momentum. This right-hand side is the change in momentum. This left-hand side is my impulse. If the change in momentum is the same, that means the impulse is the same. Now, that impulse could either be a short time and a big force, or a big time and a small force. So the way I like to think about this is the average force on an object is going to be equal to the change in momentum times the time over which that momentum is changing. So going back to this example problem, that's not it, clicker question, sorry. If the paratrooper ends up at rest, the change in momentum of the paratrooper is the same whether it takes place over a long time or a short time. But looking at this F_av equals the change in momentum over delta t, if the time is increased because of the snow, the bigger the time, the smaller the average force is going to be. So in this case, the impulse stopping the paratrooper was the same because the change in momentum of the paratrooper was the same. But if the time is much, much, much longer because of the snow, then the average force is going to be much smaller. So the answer is, what are we looking for? Does the snow? So the answer is D. It doesn't change the impulse, but increasing the time decreases the average force. So I want to touch on this a little bit because this is interesting. So average force equals the change in momentum over time. So here's an interesting thing to think about. In a collision where the object is brought to rest, the change in momentum is the same, whether the collision takes place over a long time or a short time. But the greater the time, the smaller the average net force. Pretty much any kind of padding really takes this into account. So when you're decreasing momentum, the longer the time that you take to decrease the momentum, the smaller the average net force. So for example, a few examples. Let's say we're doing a little egg toss, where I toss you an egg and you have to catch it. Anytime you do an egg toss, how do you catch it? You're always sort of catching it and then cradling it. Why? I'm decreasing the momentum of the egg over a longer time, which means the average force on the egg is smaller. This is also why we have padded dashboards, airbags. What is an airbag? Rather than you hitting the windshield and coming to rest super fast, the airbag is just extending that time, maybe by a factor of 10, which decreases the overall average force by a factor of 10. And I don't remember if I mentioned this in class or not, but crumple zones. Cars used to be built like tanks, and the thinking was the more rigid the car was, the safer the occupants inside the car will be. But if a car doesn't sort of have any give, that means if you have a head-on collision, you're coming to rest unbelievably quickly, which means the force on you is huge. Well, now cars are built to have crumple zones. And I can't draw, but cars are built to have some kind of structural weaknesses, so that if a car has a head-on collision, the front of the car will sort of collapse like an accordion, and that will cause the time to be bigger over which you're being brought to rest, which will lower the average force. And in fact, some really good NASCAR cars are designed to not only have a crumple zone, but they're designed so that in a head-on collision, the engine can actually drop out of the car, so the entire front of the car can collapse, and that just increases my time, which decreases my average force. A couple other ones. One, dynamic ropes for rock climbing. So I'm big into rock climbing. The ropes that they use are phenomenally designed in terms of engineering. They're meant to stretch. And interesting thing, if a rope didn't have any stretch to it, just falling maybe 2 or 3 or 5 feet could be fatal, because if there's no stretch to the rope and you're falling and the rope stops you, it's going to bring you to rest in an unbelievably short amount of time. The force on you would be tremendous. So even falling like 5 feet on a rope that didn't have any stretch at all would most likely break your back. So the climbing ropes are meant to stretch, and in fact, the higher up you are, even though it's sort of counterintuitive, the safer you are, because the more rope there is, the more stretch there will be, so you'll be brought to rest over a longer time. And even things like padded exercise mats, right? If you go to a dojo or something with padded exercise mats, what's the whole purpose? Bring you to rest over a longer period of time. Don't remember if I showed you this demo of throwing an egg in a sheet, but one of the demos I would have done is you can have I think I did, anyway, not sure, but you can have, I could throw an egg pretty much as fast as I can, and you can catch it in a bed sheet. And I just would have 2 people holding the sheet, and I would literally throw this egg at 60 miles an hour, hits the sheet, and it's just going to end up sliding down. It won't break because the sheet is acting like an airbag. All an airbag is doing, extending the time, which decreases the overall average force. All right, so what I want to do is one example problem. Let me just check on the chat real quick. Let me stop this share. Chats. Wait, where'd the chat go? I didn't see a poll. What questions asked about what should we think of average force? In my physics 10, you missed the sheet. I've done this demo many times, and a couple times I've had some interesting things happen. So in terms of average force or not, the question will be very specific in terms of whether it's asking for what is the average force or the maximum or something like that. I'll do an example problem or 2. So let me actually just do one example problem, and then I want to move on to conservation of momentum. Bam. Example problems. Okay, this is example problem 11.8. It says a 2-kilogram object is moving to the right with a speed of 1 meter per second when it experiences the force shown in the figure below. What are the object's speed and direction after the force ends? So here we have a plot of force in the x direction versus time. And I know that from the impulse momentum theorem, basically says that the integral of fx dt from my initial time to my final time equals my change in momentum. So equals my final momentum in the x direction minus my initial momentum in the x direction. This impulse is really just the area under the curve. So in this case, my impulse is the area under the curve. I basically have a rectangle where the force here is -2 newtons. The time is 1 second. So my area would be -2 newtons times 1 second. My area would be -2 Newton seconds. So 1, the unit of impulse is the unit of force times the unit of time. It's the Newton second. The unit of momentum is the kilogram meter per second. Those are equivalent. a Newton second equals a kilogram meter per second. However, we always use kilogram meter per second for momentum. We always use Newton second for impulse. So what I get here is my final momentum in the x direction equals my initial momentum in the x direction plus this impulse. Let me just write it like that. We just found that the area under the curve was -2 Newton seconds. Here, my initial momentum was my mass, which was 2 kilograms, times my initial velocity, which was 1 meter per second. So what I get is, since the impulse is -2 Newton seconds, my initial momentum was 2 kilogram meters per second. What I get is my final momentum is 0. And so the object ends up coming to rest. And you know what? I don't like this problem because the object comes to rest. Let me just do this exact same problem, but let me change the value of the force a bit. So let's go to April 16th, do the same thing again. So going back, example problem, it was a 2 kilogram mass moving at 1 meter per second to the right. So same exact problem, I'm just going to change it a bit. 2 kilogram moving at 1 meter per second to the right. And let's just say it experiences a force, but rather than this force being -2, let's just change it to -4. So now the force as a function of time, here's the force in the x direction. So it's, again, let's assume that the force is acting for 1 second, but let's just say that this force is -4 newtons. And I want to know, again, what is the final velocity of this, whatever this was. What was it? It was an object. Ooh, very interesting. So again, I know that the integral of fx dt from my initial time to my final time is equal to my final momentum in the x direction minus my initial momentum in the x direction. This is the area under the curve. So now my force is -4 newtons. My time is 1 second. Now my area is going to be -4 Newton seconds. I just changed it a little bit so we could actually get a value for the velocity. So what I now know is my final momentum in the x direction. Let me just get rid of these arrows since we're being specific that it's in the x direction, equals my initial momentum in the x direction plus this area under the curve. So my initial momentum was 2 kilograms times 1 meter per second. The area under the curve was -4 Newton seconds. So again, a kilogram meter per second and a Newton second are equivalent in terms of units. So what I get is my final momentum then is -2 kilogram meter per second, but that has to equal my mass times my final velocity in the x direction. So my final velocity would be -2 kilogram meters per second divided by the mass, which was 2 kilograms. My final velocity would be -1 meter per second. What does that mean? It means this force ended up reversing the direction of the object. Now it's moving at 1 meter per second in the opposite direction. All right, I want to stop this for 1 second, open up for questions. So we are pretty much done impulse momentum theorem. What I want to do now is conservation of momentum. Omar, you got a question?
Joe, can you quickly go back to the problem?
Yes, share screen. Yes. This one or the one that I just did where I changed the numbers?
And the one that you just changed the numbers.
So here I just assumed it was still moving to the right at 1 meter per second, but now the force, rather than being -2 newtons, I just changed to -4 newtons. So my impulse is greater. So it had enough force Before it just stopped it, but now I increased the force just so we could do this again. And now the end result is the object has a final velocity of -1 meter per second, which means now it's moving to the left at that speed. Okay,
Thank you.
you're welcome. So what I want to do now is just go to conservation of momentum. And I want to just give you a little preview. Conservation of momentum. And here's what conservation of momentum says. If the sum of the external forces acting on a system is 0, then the change in momentum of the system with respect to time is 0, which means my final momentum is going to equal my initial momentum, where these are the total momentum of the system. So that's what conservation of momentum says, is basically not that there's no external forces, but if all the external forces acting on a system add up to 0, the momentum of that system doesn't change. So let's just derive this because it's kind of a cool derivation. So one, keep in mind your system, just like before, you get to define your system, and it's just a defined collection of objects. So let's just say I have maybe 5 particles, and they're all moving in different directions. And I define my system as all 5 particles. One total momentum of a system. And it's kind of hard to do on here, but generally total momentum is written as a capital P. The momentum of a single object is written as lowercase p. So the total momentum of a system would be the sum of the momentum of all the objects in the system. So in this case, if I have 3 objects and I want to know what is the total momentum of the system, I would just add the momentum of all 5 objects together, and that gives me the total momentum of the system. So thinking along those lines, I have a clicker question for you. Clicker question is this. Can a single object have kinetic energy but no momentum? Can a system of 2 objects have non-zero total kinetic energy but 0 total momentum? So I have a single object. Can that object have kinetic energy without having momentum? And now for a system of 2 objects, could that system have a non-zero kinetic energy but 0 total momentum? So let me try this polling one more time. Polls, end polling, relaunch polling, continue. If I move this out of the way so I can see it, and then share screen again. Okay, now I can see it. So what do you think? Question 11.2. Can a single object have kinetic energy but not momentum? Can a system of 2 objects have non-zero kinetic energy but 0 total momentum? What do you think? Take about 30 seconds. If you can see the poll, please try clicking it in. Just A, B, C, or D. All right, going to end this in about 10 seconds. Can a single object have kinetic energy but no momentum? Can a system of 2 objects have non-zero kinetic energy but 0 total momentum? Right now we've got C is ahead with 48%, 47%, 48%. Going once, we're going to stop this. Going twice, and in fact this is not recap anymore, this is new material. All right, I'm going to stop this poll. Oh, it says share results. Oh, if I share results, can everybody see the results of the poll?
Yes.
Yes.
Oh, excellent. All right, so C is the majority answer. The C, can a single object have kinetic energy but no momentum? The answer is no. If the object has kinetic energy, it's moving. If it's moving, it has momentum. Now, can a system of two objects have non-zero total kinetic energy but zero total momentum? The answer is yes. Momentum is a vector, which means I need to take into account direction. So if I have two objects, let's say they have the exact same mass, but they're moving in the exactly opposite directions at the same speed. So maybe these each have a mass of 1 kilogram, and they're both moving to the left and right at 2 meters per second. If I were to calculate the total momentum of this system, it'd be the momentum of this first one, 1 kilogram times 2 meters per second, plus the momentum of the second guy, 1 kilogram. But I have to include a negative sign for the velocity because momentum is a vector, which means it has a direction. So if something's moving to the left, the velocity is negative, which means the momentum is negative. So here, the total momentum of the system is 0, but the total kinetic energy is not. Kinetic energy can never, ever, ever be negative. So if I have objects that are moving, there's no way the kinetic energies could ever cancel out. They're always positive. So, system. If I want to look at the total momentum of the system, all I'm doing is adding up the momentum of all the objects in the system. So if my system has 5 objects, my total momentum is just the momentum of all 5 objects added together. Now, before I go on to the next part, let me mention something to you. Does anybody know how Newton actually published his second law? And the answer is not sum of the forces equals ma. So does anybody know how that was originally published in terms of his Principia Mathematica? Newton didn't publish his second law as sum of the forces equals ma. He published it differently. Let's see what this chat says. Chat. God, I can't access the chat. It's kind of annoying me. Okay, so the answer is the way that Newton actually published his second law is the sum of the forces equals the change in momentum with respect to time. Now, these two are equivalent if the mass of an object is constant. So one, keep in mind, momentum is defined as mass times velocity. So the sum of the forces equals the change in momentum with respect to time is actually the derivative with respect to time of mass times velocity. And you have to use the chain rule. So this is actually m times dv dt plus v times dm dt. This is really how Newton's second law should be. It's just that we have always been considering that an object's mass does not change. So always when we've been doing Newton's second law, we've never considering an object whose mass changes. And in fact, we're not going to do that in Physics 4A this semester just because it's one of those supplemental topics. But it comes up oftentimes when dealing with rockets. It ends up that 90% of the mass of a rocket is the rocket's fuel. And as a rocket is being launched up, its mass decreases dramatically. So if I wanted to use Newton's laws to solve something about the problem of a rocket moving upwards, I would have to take into account the fact that the mass of the rocket is also changing. Okay, so anyway, the point is I can write Newton's second law now as the sum of the forces equals the change in momentum with respect to time. This I could apply to a single object. So if I look at the sum of the forces on an object, that will equal the change in momentum of that object with respect to time. Well, what happens if instead I have a system? And again, let's just consider our system to be those 5 particles. Well, I can apply Newton's second law to every single particle and basically say the sum of the forces on particle 1 plus the sum of the forces on particle 2 plus the sum of the forces on particle 3 plus the sum of the forces on particle 4 plus the sum of the forces on particle 5. I probably should have just used 2 objects. Equals the change in momentum of object 1 plus the change in momentum of object 2 plus the change in momentum of object 3 plus the change in momentum of object 4 plus the change in momentum of object 5. And these should all have little vector signs on them. Okay, so Newton's second law, sum of the forces equals the change in momentum with respect to time. True in a single object. If I have a collection of objects, I can just apply Newton's second law to every single object, add them all together, and what I get is the sum of the forces on every object in the system equals the change in momentum. Well, this left-hand side is really just the sum of the forces on the system as a whole. And this this right-hand side, I'm going to write as the change in momentum, or the change with respect to time of P1 plus P2 plus P3 plus P4 plus P5. Well, if I add up the momentum of every object in the system, this is just the total momentum of the system. So the end result is, what I have right now is, if I look at the sum of the forces acting on a system, that's going to equal the change in momentum of the system. And let me just write SYS here, just to emphasize that this is the total momentum of the system. Now, here's where this gets a little bit fun. Just like before, I have my system. Anything that's not the system is the environment. And any forces that the environment exerts on the system is an external force. So my system, I can consider to have both internal forces. Well, actually, let me do this a different way. I'm going to consider the sum of the forces on the system to be 2 separate sets of forces. I'm going to look at first the sum of all the external forces on the system, just call this external, plus the sum of all the internal forces on the system has to equal the change in momentum of the system. So internal forces, these are forces system exerts on each other. So in the case where I have 5 particles, any forces these 5 particles exert on each other are internal forces. External forces are forces the environment exerts on the system. So forces environment exerts on the system. So here's a really interesting point. One of these terms is always going to have the exact same value. And therefore, we can ignore it. Question I have for you is, which of these 3 terms can I ignore because it's always going to have the exact same value? And what is that value? Meaning, can I tell you what the sum of the external forces is always going to be on any system? Can I tell you what the sum of the internal forces is going to be on the system? Can I tell you what the change in momentum of the system is going to be? Anybody have a thought on, let me just stop this for 1 second, which of those terms is always going to give me the same answer? And actually, I'm probably not even asking that, right? Let me just go back to the screen share. If you remember, what does Newton's third law say? Oh, let me get this. Newton's third law was basically for every action, there's an equal and opposite reaction. Or in terms of 2 particles acting on each other, it basically says the force of 1 on 2 equals negative the force of 2 on 1. What this means is that if I look at a system and I add up all the internal forces acting on the system, they have to add up to 0 by Newton's third law. If one object exerts a force on the second object, the second object exerts the exact same force, but the exact opposite direction. So when I go and I look at all of these forces that particles might be exerting on each other, if I add up all the internal forces, it always has to be 0 by Newton's third law. So the sum of the internal forces on a system is always 0 by Newton's third law. What that means is when I look at the sum of the forces on a system being equal to the change in momentum of the system, and I break these forces up into, they're either going to be internal forces or external forces, right? Those are the only real two. I either have things in the system exerting forces on each other or things outside the system exerting forces on the system. That equals the change in momentum of the system. And the sum of the internal forces is always going to be 0 by Newton's third law. It has to be. So this isn't conservation of momentum, but I've reduced this to the sum of the forces on a system from outside the system. Sum of the external forces equals the change in momentum of the system. So this left-hand side is all external forces on the system. This right-hand side, P, is the total momentum, P, of the system. So if I had 5 different objects, I need to look at the total momentum of all 5 objects added together. So this equation is basically what conservation of energy comes out of. And it's this. If this left-hand side, the sum of the external forces is 0, then the right-hand side is 0, which means the change in momentum with respect to time of the system is 0. So conservation of energy, conservation of momentum says the following. If the sum of the external forces on a system is 0, then the change in momentum of the system with respect to time is 0, which means my final momentum is equal to my initial momentum. And that's what conservation of momentum says. And let me tell you, conservation of momentum is really, 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 really useful because I can use conservation of momentum during collisions. And the reason it's so useful is we know that during a collision, heat is generated. And so it's really hard to use conservation of energy when I have objects physically colliding together, because it's hard to figure out exactly how much heat was generated, how much energy was lost to sound, and so on. But momentum is always going to be conserved during a collision because I can define my system as 2 objects, and when those 2 objects collide, the forces they exert on each other are internal forces. And so as long as there's no external forces acting on it, momentum will be conserved. So let me just do one example problem that I'm going to make up, and then I'll kind of roll into office hours. So let's just say that I've got 2 objects moving towards each other. One of them has a mass of 10 kilograms, and let's just say it's moving at 5 meters per second. The other one has a mass of, let's say, 5 kilograms, and it's moving at 4 meters per second to the left. Then they collide, and let's say they stick together. And the question is, after they stick together, how fast are they moving, and in what direction are they moving? So both of these objects, you know, they're on some kind of floor. Let's just say it's frictionless floor. So frictionless surface. Now, one thing about conservation of momentum, kind of like energy, it's if the work done by all external forces is 0, then energy is conserved. It doesn't say that there's no external forces, just that the total work done is 0. Same thing here. It doesn't say there's no external forces acting on the system. It says they all add up to 0. So if I define my system, let's say as the 2 blocks, or these 2 carts, then the external forces, what forces are acting on these carts? Basically, I've got the normal force and I've got gravity. But if there is no acceleration in the y direction, these 2 forces are going to be equal to each other. The normal force pushing up is going to be exactly equal to the force of gravity pulling it down. So the sum of the external forces is going to be 0, which means that the final momentum of this system is going to equal the initial momentum. Well, momentum of a system is just equal to the momentum of all the objects in the system added together. So in this case, I only have 2 objects, so it would be m1 v1 plus m2 v2. So if momentum is conserved, then I know that my final momentum of the system has to equal my initial momentum. Well, if these 2 things stick together and move as one after the collision, they basically have the exact same velocity. So I could call my initial momentum m1 plus m2 times my final velocity. Did I label these m1 and m2? Let's just call this one m1, this one m2. Before the collision, the initial momentum is m1 v1 initial plus m2 v2 initial. So initially they each have momentum, then they collide, stick together, and move off. Since the sum of the since the sum of the external forces is 0, the total momentum of this system is conserved. So really, conservation of momentum is all about setting up this equation that says my final momentum after some collision or something happens equals my initial momentum. Since they stick together after the collision, they're both moving at the same final velocity. So my final momentum is m1 plus m2 times my final velocity. So what I'm looking for is, in this case, what is my final velocity? So I could just solve for v final equals m1 v1 initial plus m2 v2 initial over m1 plus m2. Now, here's the mistake that people make all the time. And you'll probably on the celebration have a very simple problem like this, is that momentum is a vector that depends upon velocity. So if something is moving to the left, in this case, the velocity, I have to write as -4 meters per second. If I have the velocity as 4 meters per second, that basically means the object would be moving to the right. So in this case, my m1 is 10 kilograms, m2 is 5 kilograms. My initial velocity for mass 1 is plus 5 meters per second. My initial velocity for mass 2 is -4 meters per second. So when I plug in these values, what I get is, I just lost my 10 and 5, 5 and 4. So I have 10 kilograms times 5 meters per second plus 5 kilograms times a -4 meters per second divided by 15 kilograms. What does that end up being? I've got 50 plus -20 is 30 divided by 15. What I get is 2 meters per second. Hey, those numbers worked out nicely. Now, you could have sort of figured out before what direction this thing is going to move afterwards. How? Well, initially, mass 1 had a total momentum of 50 kilogram meters per second to the right. Mass 2 had a total momentum of 20 kilogram meters per second to the left. So the system has more momentum, in a sense, moving to the right than it does to the left, which means after the collision, the momentum still has to be pointing to the right because momentum is conserved. Booyah. Okay. So I kind of went 10 minutes, you know, I think in terms of lectures, rather than doing a 45-minute lecture followed by 30 minutes of office hours, lectures have been going a little bit longer, so it'll probably be more like an hour of lecture followed by 15, 20 minutes of office hours. So I have covered everything I want to cover today in terms of conservation of momentum. On Monday, I'm pretty much going to finish this chapter. We have covered pretty much everything that we're going to cover. We're going to talk a little bit about collisions, but key point is in any collision, I can treat my system as the two objects that are colliding, which means any forces they exert on each other are internal forces. So the sum of the external forces are 0, and I can use conservation of momentum. All right. I want to open it up. Questions on anything I've covered so far? Privately, you always have anchors with static rope and not dynamic rope if the force. Mark, why do we set anchors with static rope and not dynamic things if it decreases force? Ooh, Marco, that's a great question. I don't want to answer that in office hours, but at some point, if you want to talk about that, setting anchors and stuff like that is sort of very interesting too. But even those that webbing has a teeny tiny bit of give to it. No ropes really are 100% static where they don't have any give at all. Okay, so if there are no questions, I'm going to sort of end. So lecture. Lecture, bring in office hours. So I'm going to hang around here until 12:30. Anybody has any questions, let me know. I'm just going to sort of hang out here and